And I don't know, I think that stuff's kind of boring. Like, you can talk about isometries in general, so why do you care necessarily about what the isometries are from R2 to R2 and R3 to R3? Okay, there is a sense in which the isometries there are very well behaved, and that you know, you could probably build up some intuition by studying those things. But basically, I can tell you in like 2 lines how it works. Isometries in R3 are basically rotations and reflections, right? So again, with the idea that isometries don't change lengths, right? If I give you a vector and I want to apply a linear transformation to it without changing its length, well, yeah, a rotation definitely does that, right? It rotates the vector and it doesn't change its length. Or of course, you can reflect it. Also doesn't change its length, right? And reflections and rotations are different. And in particular, the reason why they're different is if, you know, let's say you have, you know, the x-axis and the y-axis like this, and then you reflect them, right, say through the x-axis, well, there's no way I could have rotated this to get that reflection, right? I'm gonna like break my wrist trying to do this, right? But there's no way I could have if I reflect, I can't get a rotation to affect that, or I can't get a rotation to effect that reflection. That's my little tongue twister here, effect the reflection. So they are different, but in effect, those are the only things that can happen. And in R3, it's basically the same deal, right? You have a couple more rotations. You can rotate about, you know, several different axes at once, and you have some rotations. But my mentality here is to attack this from a little bit more of a theoretical viewpoint, because when you start actually dipping into that, the language of rotations and such, it actually starts to get quite messy and quite technical. And I don't think you'd want to do that. I don't particularly want to do that. So let's approach it from a very high level space. Now, the only kind of downside of that is that when I do examples, they are probably going to be reflections and rotations, right? Okay, so first thing, we start off here with the definition of an isometry. So you've got 2 inner product spaces. So, I mean, you know, for a linear transformation, you have a vector space on either side, but now we're actually going to enforce that you actually have inner products on either side as well. And of course, they don't have to be in any way related to each other, at least at first. It doesn't seem like they have to be related to each other. So an isometry is a linear transformation then with domain V and codomain W, such that the inner product is preserved. Okay, and this is what I mean here by the inner product is preserved. Right? And if you think about what this statement actually means, it says, okay, if I have vectors and I apply t to them and I measure, you know, their inner product, well, that would have, I get the same answer as if I hadn't applied t to those things at all. So the inner product doesn't change under application of t. So hopefully that makes sense to you. You kind of have to think about it for a second, but it says the inner product does not change under the application of t. So if you've got 2 vectors, v and w, and you take their inner product, you get a number. Then if you take t of v and t of w and measure them in the inner product in the codomain, you'll also get the same number, right? So t preserves that inner product. So that's the notion of an isometry. Now, immediately what you should note, now, you know, usually we are going to be interested when t is an isomorphism, but it doesn't have to be. Okay, and I'll talk about, there are a few special cases where you'll immediately be able to establish that it is in fact an isomorphism, but you don't have any guarantee of that immediately. Okay, you don't know. All you know is that it preserves lengths, but the big thing that could fail is that, for example, the isometry could not be surjective, right? So think about it. If you have a plane, right? So let's say your domain is the plane, it's R2, and you embed it into R3. You literally just say, I'm going to take this plane, R2, and make it like the XY plane in R3. And you can see distances aren't going to change if you do that, right? Maybe let me write that example down explicitly, though it will answer one of your exercise questions today. Right, so for example, let's say I define t from R2 into R3. And let's just, again, let's do the obvious thing here and take R2 into the XY plane, right? That's what this means. So I'm going to take XY to XY0. Maybe let me write that a little bit clearer. XY0. Okay, so this is certainly a linear map. Nothing really to do there. And I also claim that if I put the Euclidean inner product on both spaces, this is an isometry. So let's endow both R2 and R3 with the Euclidean inner product. And note that these are actually different inner products, right? Because they're occurring in different spaces. Okay, so this is an isometry. T is an isometry. Right? And you can just check, like that's not particularly hard. So let's say you have, oops. And I'll give you a condition in a second to check this even faster. But let's say V is X1, Y1, W is X2, Y2, right? The thing that we want to check is that the inner product of V and W is the same as the inner product of TV and TW. Okay, so if we take the inner product of V and W, well, we know what that is, right? X1, X2 plus Y1, Y2. And then, so TV and TW, that's going to be XY0, or X1, Y1, 0, X2, Y2, 0. And yeah, that works out to be the exact same thing, right? Because the last set of terms, when you add them together, just end up giving you 0, right? Plus 0, 0 here, which I mean, if we could put it in, we could put it in if we want. But these are clearly equal, right? So this does end up being an isometry. Obviously, it can't be an isomorphism. It's not even an isomorphism of vector spaces, let alone an isomorphism of inner product spaces. But that, you know, we're starting to get an idea of what an inner product of, or an isomorphism of inner product spaces would be. It is a bijective isometry, right? So again, certainly this can't be an isomorphism. It's certainly not surjective, right? The dimensions of our two space are just completely and totally different. But nonetheless, there is an example of an isometry. Okay, so you can't guarantee immediately that the thing that you have, that all isometries are isomorphisms. And like I said, I'll tell you in a second when you can guarantee that. Maybe let's do another example though. Let me just fall back on my rotation matrices. So let theta be some angle between 0 and 2 pi. And let's define this map from R2 to R2 as multiplying XY by the matrix. And I think we've seen this before. Right. And we can just work that out explicitly if we want. X cosine theta plus Y sine theta negative X sine theta plus Y cosine theta, like so. Okay, again, claim if both spaces have the Euclidean inner product, this is an isometry. And again, this is because this is a rotation by pi degrees. In which directions? 1, 0, 0, 1, whichever direction, you guys can tell me. So pi over 2 would give me 0, 1, negative 1, 0. So I would get y negative x. So xy becomes y negative x. So this is a counterclockwise rotation. Okay, so again, this is an isometry. Why? So we already know, you can probably guess what the norm of, you know, I'm actually just going to look at, let me look at the norm just to make the life a little bit easier. So I'm not dealing with x1, y1, x2, y2. Let's just kind of look at the norm. Because, you know, if you have an isometry of inner products, it also correspondingly gives you an isometry of the norm. So if I were to, for example, look at the norm of x cos theta plus y, there's a little bit of computation to do here. I don't think it's too bad, but I might go through it just a little bit quickly because, you know, we don't want to spend forever multiplying real numbers. Okay, so if you do this, you'll end up getting, so x squared cos squared theta plus y squared sine squared theta plus 2xy cosine theta sine theta plus x squared sine squared theta plus y squared cosine squared theta minus 2xy cos theta sine theta. Okay, so the cos theta sine thetas cancel each other out. And then we get x squared cos squared plus x squared sine squared. And we know by the Pythagorean identity that's just 1. Now let's do that squared. X squared plus y squared. And yeah, that's exactly what we know the norm of xy squared is. Okay, so if you want to try this on an inner product instead and input 2 vectors, you absolutely can. I'm just kind of doing a shorthand here and computing this on the norm to show you that it does in fact define an isometry there. But yeah, hopefully you see by the magic that is trigonometry, all of these numbers work out, and this is in fact an isometry. But again, intuitively, we knew that would be true, that rotation shouldn't change the lengths of the vectors, right? The math gets a little bit nasty, but other than that, it's not too bad. Okay, and this is actually there's a nice exercise that I've set up this week that I'm gonna want you to try out. And it's actually gonna have you check that the determinant of an isometry, when you compute it, is plus or minus 1, right? So its absolute value is always equal to 1. Now, my question to you is, does anyone know why that's true? Does anyone know what the determinant of a linear transformation measures, the determinant of a linear operator? I don't know if anyone would have told you this, so I'm kind of interested to see if anyone knows. No? Nobody? Is anyone taking 232 this term? Like the second year calc course? Yeah, something to do with scaling, absolutely. Is anyone taking second year calc? Like the, and doing iterated integrals, and you see like the determinant of the Jacobian come out when you do change variable? Not quite? Okay, yeah, sure. So what the determinant actually does, the determinant calculates how volumes change under your linear transformation, right? So basically the idea is if you have a set, this is just kind of an aside thing, right? I'm not going to ask you to know this, but it's kind of nice to have an idea of what the determinant is actually telling you. So if S, let's just use Rn for now. If S is a subset of Rn, right? Then, or let's say NT maps Rn to Rn, then the volume of T of S is the determinant of T times the volume of S. Okay? So, yeah, exactly, it's the Jacobian. And the reason for that, that Jacobian, well, I'll tell you about the Jacobian in a second. But what the determinant actually does, so if you give me a linear transformation, you start with a set, and it doesn't have to be a subspace, it's just some set, and you compute its volume. And of course, you need to know what volume means, but you guys have a rough idea of what that means. So you know what its volume is in Rn. Then if you look at T of S, the exact way that the volume changes from S to T in S is described by the absolute value of the determinant. Okay, so the determinant tells you how things scale. It tells you how things change in volume. Now, in the case of an isometry, things aren't changing, right? You would expect, okay, if isometries doesn't change the lengths of angles, it shouldn't change the lengths of volumes either, right? With the idea that, you know, that volumes are kind of infinitesimally approximated by little cubes. So it actually very much makes sense that an isometry should have determinant 1, right? That if the determinant tells you how things scale, a determinant of 1 says, well, things aren't changing in size, right? They're all the same size. Now, when you do the Jacobian in stats, now that's the same Jacobian that shows up in multivariate calculus. And of course, this happens when you're doing a multivariate integral, right? And what the Jacobian is doing is now you might not have a linear transformation, right? So again, for those of you who maybe haven't taken second year calc, don't worry about this. You can listen to the fancy words, but again, none of this is examinable. But now you're given, a change of coordinates, like say from Cartesian to polar coordinates. Now that's definitely not a linear transformation, right? It's not a linear map from R2 to R2 because it's got cosines in it and sines and stuff. But that's fine, because what you can do is you can take the derivative of that transformation, that coordinate transformation, and what you get is a linear map, right? So when you differentiate r cos theta, r sine theta with respect to r and theta, you're actually differentiating that transformation, and the answer that you get out is a linear transformation, and you can take its determinant. And so what that determinant is telling you is the infinitesimal scaling change that occurs at every single point, which is why it actually shows up in your change of variables. And for those of you who now, even if you haven't taken second year calc, if you've taken first year calc, you guys might remember that when you do the substitution, so substitution becomes change of variable when you get into higher years. You guys probably remember this, like f g of u, g prime of u du, right? There's a Jacobian here, right? Maybe let me use x's and then I'll change that to u. Okay, so you guys all know how to do this substitution, right? You get f of u du, because you set du to be g prime of x dx. Okay, so thing is, there's secretly a determinant here. Okay, but the determinant is around the 1-by-1 matrix G prime of X. So you don't see it, right? Because you know what the determinant of a 1-by-1 matrix is. It's just the number itself. So really what's happening here is this is actually the absolute value of the determinant of G prime of X. Okay, so that's kind of cool that it's hiding 2 there. But more importantly now, if you've ever wondered what G prime X dx actually means, what it's actually telling you is how much you've scaled the x-axis. When you perform this integral, what G prime of X is doing to you is telling you at each point in your interval, the infinitesimal scaling change that's happening. So you can think of G prime of X as being this this linear transformation from R1 to R1, and it's telling you precisely by how much lengths change at every single one of these points. So if you've ever wondered about that in substitution, in first year calc, that's secretly what's happening, and that's secretly what's going on. Okay, so just, this is obviously a little bit of a tangent here, but that's what the determinant is very much telling you what's happening, right? It's telling you how things are changing in terms of scale. And so we see this even in calculus, right? Let alone linear algebra. So, hopefully an interesting little thing there that you can be like, oh, some of that's starting to make sense. Okay. Anyway, well, it depends on what calc prof though, right? Because I mean, your first year calc profs can't tell you this because the assumption is you don't know any linear algebra. So there is kind of, an obstruction there that you're all much now more educated and more mature, and you can, it's possible for us to tell you these things. One of these things I always talk about, yeah, I know. And again, part of that is I think 232 actually doesn't require linear algebra, right, as a prereq. Or maybe if it does, it only requires 223. I don't even think it requires linear algebra, right? I don't think there's any algebra prereq. And so again, they just kind of have to be like, here's what a determinant is, ooh, and then kind of sweep everything. Yeah, exactly. And so they sweep everything under the rug because they have to, because there's no algebra prereq. And yeah, I always say it's kind of a real shame, because if you guys didn't know, the entire point of multivariable calculus, what you do is you say, oh, I've got this nonlinear function, right? And what the derivative should be is the best linear approximation to that function, right? And you know that, right? If you've got a curve and you want to take, that the derivative at each point is the slope of the tangent line, right? There's a sense in which it is the best linear approximation, right? That's what the derivative gives you. So when you get to maps of Rn to Rm, which I don't even think you do in 232, I think you just do Rn to R. But when you get from maps to Rn to Rm, you'd say, oh, the derivative should be the best approximation to that function. But you know what a linear transformation from Rn to Rm looks like. It's an m by n matrix. So like the whole point of multivariate calculus is to reduce it to the study of linear algebra. So the fact that somehow we're teaching like multivariate calculus without linear algebra seems a little bit crazy, right? But again, there are ways you can get around that and kind of not have to worry about it. But strictly speaking, you should have linear algebra when you do a multivariate calculus course, because the entire point is to reduce it to the study of linear algebra. So yeah, you know, I think only now you guys are kind of very tangentially seeing how they're related, because I can't go into it too deeply because calc isn't a prereq for this course. So right now they kind of live in isolation from each other, but they actually are very closely related and intimate. It's just, you won't really get the opportunity to see this unless you take some higher level math where you can properly kind of marry them and see how that works together. So it is a fun and cool thing to really see how this works out. Okay, so anyway, that was a long kind of side tangent thing, but you know, just to hopefully encourage you that, you know, all of this stuff is related at the end of the day. So I have here proposition 427, and so proposition 427, you know, we've seen something similar to it in terms of just linear transformations, but now this is specifically for isometries. So it says, if you have a linear operator, and I really want to highlight this right now. So when we do this, we're talking about linear operators, right? So domain and codomain are the same. Okay, we're not talking about isometries from V to W. We're talking about, you know, isometries from V to V. So the following are equivalent. 1, you're an isometry. 2, you map orthonormal bases to orthonormal. I think this should here say orthonormal. I'm sorry that I made a little typo there, but that should say orthonormal. So, and 2 and 3 are basically the same thing. So I don't want you to worry too much about their distinction. You're an isometry if and only if you map orthonormal bases to orthonormal bases, if and only if you preserve the length of vectors, right? And that's what number 4 here is saying. Number 4 here says you preserve the length of vectors, okay? And I cheated a little bit, right? I was using number 4 when I did this example up here with x cos theta plus y sine theta, negative x sine theta plus y cosine theta, right? I was really using number 4 there because I was just checking the norms. But hopefully, you know, you guys have done the reading and will forgive me of that. But that's what I was using there. But okay, so that's a very reasonable thing. And then again, we had a similar theorem like this for linear transformations, right? A linear transformation is an isomorphism if it mapped a basis to a basis. But now we have a more specific restriction. It's not enough to map a basis to a basis. You have to map an orthonormal basis to an orthonormal basis. Okay, so that's kind of how that changes. And we know that not all isomorphisms are isometric isomorphisms. Okay, now this isn't too hard to prove, and I suggest that you go through it and at least prove 1 or 2 of them just to get you know, familiar with working with isometries. None of them are terribly difficult, so it's a good place to kind of, you know, ground yourself and root yourself and try some exercises. Now, what I do want to say here as a little note, okay, so this is, again, I highlighted that this is for operators, right? Remember, operators map V to themselves. However, this theorem does naturally extend to general isometries as long as both isometries have exactly the same dimension. However, theorem holds for T mapping V to W so long as dim V equals dim W, okay? So the theorem, right, basically you can replace the codomain with a different inner product space. And this theorem will still be true, but you have to add in 1 additional condition, which is that the dimension of V is equal to the dimension of W, okay? Now, I'm telling you this because actually this is probably the right exercise. So let's say prove this. Okay, this is good practice. I want you to restate proposition 4.27, but now change the codomain to being an arbitrary inner product space of the same dimension as the domain, and reprove the theorem. The theorem is word for word identical with the appropriate changes, right? Anytime that you're working in the codomain, change V to W, change the inner product in V to the inner product in W, okay? So word for word identical proofs, but so do that as an exercise. And again, you'll get that idea of kind of grounding yourself in isometries, and you'll have actually proven your own theorem. You can just, like I said, you can take from me and trust me if you want, that this is true if you change, make these appropriate changes. But I'd recommend that you give that a try. Okay, and so there's lots of cool things that we can do here. So as an immediate corollary to this, so if V and W are inner product spaces, with the same dimension, right? So dim V equals dim W, and T mapping V to W is an isometry, then T is an isomorphism. Let me get rid of this thing. Oop, no, that's the wrong way. Okay, so you might have to think about what this is saying for a second. What this is saying is that an isometry between two vector spaces with the same dimension is automatically an isomorphism. That's not true of linear transformations, right? With a linear transformation, I could map, for example, Rn to Rn with the zero linear transformation, right? It just maps everything to zero. That's a linear transformation. It's definitely not an isometry. So isometry is that additional structure of requiring that they, for example, map orthonormal bases to orthonormal bases is enough to guarantee that any isometry between two vector spaces of the same dimension is automatically an isomorphism. Okay, so that is a stronger result than with linear transformations by themselves. And the proof of this fact, the reason why it's a corollary, is just 427, number 2 here, right? If you have an orthonormal basis, it maps to an orthonormal basis. And that, again, minus the orthonormal part, is precisely what it means to be an isomorphism, right? Isomorphisms map bases to bases. So an isometry is going to map an orthonormal basis to an orthonormal basis, but in particular a basis. So it must be an isometry. But this only works if the dimension of V and the dimension of W are the same, right? Because I gave an example above of this map from R2 to R3 here at the top of the screen, where this is an isometry that doesn't map an orthonormal basis to an orthonormal basis. What fails? Precisely that the dimensions are not the same, right? You got R2, a dimension 2 vector space on the left, and you got R3, a dimension 3 vector space on the right. So dimensions have to be the same. Okay. So hopefully that helps you there. Let me, I just do want to do one more example of an isometry here that is really important and that we're going to use a lot. So actually, if you remember, so recall from week, I think it was week 10-1, you showed the following. Okay, so the idea was, let's say you have an inner product, finite dimensional inner product space V. Finite dimensional inner product space. Okay, and sometimes we'll say inner product space, but not like write down explicitly what the inner product is. In that case, we're saying, it's an inner product space. I don't have to write down, what the inner product actually looks like. It's the left angle bracket and the right angle bracket. You just know it's there, right? the BV finite dimensional inner product space. Then, so you should have shown, oh, then if B is, and let's say orthonormal for this one, orthonormal basis. Do you remember this statement, right? Where C beta is our usual coordinate transform. So let me write this in a slightly different way. So this is the inner product in V. And this is the Euclidean inner product in Rn. Okay, so I think this was actually question 1 of the week 10-1 exercises that we did. So it would have been this time last week that we were doing it, and I had you prove that this was true. And the proof isn't terribly difficult. But notice that this exactly tells you that CB is an isometry. And not only is it an isometry, it's an isometry between two vector spaces of the exact same dimension, right? That's the entire point of the coordinate transform. Therefore, it's an isomorphism. Is an isometric isomorphism. Right? So immediately, you always know your coordinate transforms are isometric isomorphisms into Euclidean Rn. That's super useful and a super powerful result. So I want to make sure that you internalize that. If you ever need to produce examples of isometries, this is a great way of doing it. Fix an orthonormal basis, take a look at your coordinate transforms. And then the fact that they are isometric isomorphisms is going to be very important for the next couple of results that we're going to have. Okay, so I want you to think about that and make sure you have that internalized in your brain. The coordinate transformation is always an isometric isomorphism. And at some point, I suspect some of you are going to get confused because you have so many results hanging around in your head. You're like, okay, wait a second, what the hell is going on? CB is an isomorphism. You know that's true. That's always true. The coordinate transformation is always an isomorphism. When is it an isometric isomorphism? Okay, when we have an inner product space and the basis is orthonormal. Okay, great, that works. So you can actually check if the basis is not ortho, or at least not orthogonal, it's not an isometric isomorphism. It's just an isomorphism. So you can actually check just by doing a computational example that if you don't take an orthonormal basis, this doesn't work out. But kind of the other thing that I want to say here is when you're going through and you're studying, and especially for the final exam, you're going to see all these facts that you know about the coordinate transform. And now we're talking about a bunch of facts that, oh, if you're working with an orthogonal basis or an orthonormal basis, these additional things are true. And it's going to be, it can be quite confusing because the results seem very similar, but on the isometry side of things, you've added a couple of conditions, usually orthonormality of your basis, and it results in a slightly stronger restatement of the theorems that are over here. So you might want to, at some point, just make sure and you go through and are able to distinguish those results. And are very clear about what is stating what when, if that makes sense, right? Because again, we have like, 5 or 6 results over here on coordinate transformations. We have those same 5 or 6, but with the addition of an orthonormal basis, and that's going to change things just a little bit, but enough to potentially screw you up. So go through and make sure that you're, sorting those things out and are comfortable with their differences. Okay, so, oh, out of curiosity, is anyone taking, I suspect not, but is anyone taking Michael Groschenig's Lie Algebras course this term? Are any of you taking it? Because I know it's a very weird course because usually to take Lie Algebras, you need to be in grad school to take a Lie Algebra course, but for some reason it's currently a 3rd-year course, so I with like no prereqs, so I have no idea who's taking it. Okay, so I will take your silence as an indication that you're not. So there's a 3rd-year course. I don't remember what it's called, but it's like 387. and it is a mathematical course on Lie algebras. Lie spelled like lie, right? That's how you pronounce that. If you see that word in mathematics, L-I-E, it's pronounced Lie. Okay. So we have a third year course in Lie algebras, and I'm just wondering if anyone's taking it, and I suspect not. But I do know there are a couple of students who are taking it. There's like 15 people enrolled in that class. Anyway, it's a bit of a stretch, but I suppose not. And I'll tell you why, though. That's an interesting thing. So, is anyone taking group theory? Is anyone taking 301? Math 301? Maybe next year, next term? Okay. So you two. So Vish. Okay, so you three. So those who have, said you're taking group theory, I want you to pay attention to this thing that we're about to define. So we say that an n by n matrix is orthogonal if A transpose A is equal to the identity, or equivalently if A times A transpose is the identity. Okay. So first of all, can anyone give me an example of an orthogonal matrix that is not the identity matrix? Okay, do it 2 by 2. Can anyone think of a 2 by 2 matrix that is orthogonal but not the identity? So A transpose times A is equal to the identity. No one? Yeah, absolutely. That's a nice little twist on the identity, but yeah, 100%, that one works. Okay, how about this one? Okay, so here are 3 examples, and there are many more. There are, in fact, infinitely many. Here are 3 examples of orthogonal 2 by 2 matrices. Now, this might not be enough for you to all recognize the pattern, but what can you tell me about the columns of an orthogonal matrix? Product of all the elements is 0. Well, except for the columns with themselves, right? Okay, yeah, so Yunkai, you've kind of noticed they're all invertible, right? I think that's what you're saying. And it's true, they are definitely all invertible. Vishnu, so the product of all the elements is, okay, yeah, so there's definitely a determinant statement here as well. You guys remember, you might not, but remember how, like, when you first defined matrix multiplication, you define it as the dot product of the rows of the matrix on the left and the columns of the matrix on the right, right? So when I write out that A transpose A, what I'm doing is I've written the columns of A, but when I take the transpose, the columns of A become the rows of A, right? And then I'm going to take a bunch of dot products. This might require a bit of thinking because it's hard to actually draw this. But what you end up getting is the resulting matrix is, C1.C1, C2.C1, Cn.C1, C row 1, column 2, C1.Cn, you remember this stuff? Okay. So the way that you actually compute matrix multiplication, right, is you take a whole bunch of dot products between the rows on the left of the matrix on the left and the columns of the matrix on the right. So look at the resulting matrix, right? The resulting matrix is a bunch of just dot products of the columns of A with itself. But as Vishnu kind of pointed out, what you end up getting is that all the C2.C1 or C3.C2 or anything like that, those all have to be 0. Right? And if I is equal to j, namely along the main diagonal, they're all equal to 1. So what are the columns of the matrix A? What are they as in Rn? Think of them, the set of columns. Well, you don't want to say they're right, because this matrix here, for example, isn't diagonal. Right, this 1 over root 2. Right, exactly. They form an orthonormal basis. Okay, so there is a perfect bijection between the set of orthogonal matrices and the ordered orthonormal bases of Rn. They are the same thing. If you give me an orthonormal basis of Rn, I'm going to form a matrix with whose columns are the basis vectors. That is an orthogonal matrix. Conversely, if you give me an orthogonal matrix, then its columns are an orthonormal basis for Rn. Okay, so orthogonal bases and orthogonal matrices and orthonormal bases are the same thing, right? Just smushed together in matrix form. Okay, does that make sense? That's why I was able to check without doing any matrix multiplication whether the examples that you gave me were in fact orthogonal, and why I was able to produce this 1 over root 2 example off the top of my head, because I knew that these were, the columns were an orthonormal basis, right? Okay, so orthogonal matrices correspond to orthonormal bases. And again, try it out. Just choose your favorite orthonormal basis, smush them together into a matrix, and check that, in fact, it ends up being an orthogonal thing. Now, the reason why I mentioned groups in Lie algebras is for those of you doing group theory next term, the set of all orthogonal matrices is a group. And it's a group that you probably won't discuss in 301, but it's a super important, super cool group. So you might just want to write a little star here and remind yourself to check this once you've learned group theory, but this is actually a group. Okay, now the reason why we want to talk about orthogonal bases or orthogonal matrices is the following. Proposition 429 says, well, let's say that I give you a finite dimensional inner product space and a linear operator. The following are equivalent. T, and again, 2 and 3 are basically the same thing. You're in isometry if, whenever you give me an orthonormal basis and you compute the matrix representation of T in that orthonormal basis, the thing you get out is orthogonal. Okay, so if you work in an orthonormal basis, the matrix you get out will be orthogonal. Okay, the proof of this is incredibly straightforward. Okay, the proof is absolutely trivial, basically. So, and I'm going to let you prove, 3 implies 1, but the proof of 1 implies 3, that if you're in isometry, then your matrix representation is orthogonal. So if T is an isometry, then, okay, so the columns of MBT right? We're all pros at this because we've done this a million times. They are C, B, T, B, I, right? For I equal 1 through n. Okay, so what we want to show is that these things, which are the columns of the matrix representation, are all orthonormal, right? So what we want to do is look at their dot products with each other. And you're looking at this, you're like, okay, this is a nightmare, right? This is gross. And let's just remind ourselves, this is an Rn. Okay, but we already said the coordinate transform with an orthonormal basis is an isometry. Right? And then T is also an isometry. And this is, yeah, exactly what you want it to be. 0 if I does not equal J, 1 if I equals J, right? So we've shown that the columns of the matrix representation are in fact orthogonal and unit vectors, right? So they're orthonormal. And that's the proof. That's the whole proof. It's just, you know, the coordinate transform is an isometry, and you assume that T was an isometry to begin with. So you can just kind of peel these things off like the layers of an onion until you get to that juicy center of the onion, which nobody thinks that that's true. But anyway, until you get to that kernel inside of the onion, which is this statement, that the BI, taking the inner product of the BI and the BJ, and you see, well, that was orthonormal by assumption. So, you know, we're done. We get what we want. And this also in particular shows you that if you don't take an orthonormal basis, that this isn't going to be true, right? Because even if you can peel off the coordinate transformation, which you generally can't, even if you can peel it off, if you didn't start with an orthonormal basis, when you get to this point, you won't be able to say that there's 0 if I is not J, right? But that's the proof of 1 implies 3. The proof that 3 implies 1 is very straightforward. It's very easy, so don't worry about it. Like, go through it as an exercise, right? But it's not terribly difficult. But there it is. So if you can, and again, kind of the fact that these are equivalent mean that if you can find any basis in which the matrix representation of T is an orthogonal matrix, boom, you know it's an isometry, right? So if you want to prove something is an isometry, it suffices to find a basis in which its matrix representation is an orthonormal basis, right? So you can do that. Yeah, okay, so that helps. Now, I don't think we're going to get to the exercises this week because there's only a couple of minutes left. But one thing, you know, Vivi was kind of mentioning there does seem to be this something about the determinant going on. Well, I already told you that the determinant of an isometry is always plus or minus 1. And you know that the determinant of an isometry is the same as the determinant of its matrix representation, right? In fact, that's the definition of the determinant of a linear transformation. It's to choose some matrix representation and compute its determinant, and you know that doesn't depend on which basis you chose. So what you should be able to prove very, very quickly is that the determinants of the orthogonal matrices are also always plus or minus 1, right? Or conversely, once you know that the determinant of an orthogonal matrix is always plus or minus 1, use that to prove the result about isometries. So that's one of the exercise questions for this lecture, which I recommend that you try and do. It's very quick. It should only be a line or two, but prove that isometries have determinant plus or minus 1. And then therefore, so do the orthogonal matrices, or do it the other way. Prove the orthogonal matrices have determinant plus or minus 1, and use this to prove that the determinant of the corresponding linear transformation has determinant plus or minus 1. Okay, so let me know if you have any questions. Hopefully, you've got a good feeling for isometries. I think a good exercise as well, try and write a couple of them down. They actually are surprisingly tough to write down. It's like, again, a good kind of source for isometries is the coordinate transformation, but they turn out to be quite hard to construct in general. So don't beat yourself up if you're having trouble constructing them, but see if you can write down a few just as a good sanity check to make sure that you understand what's going on. Okay, otherwise that's going to cover it for today. I will see you on Thursday. Your readings for Thursday are 4.4, which is a very short section. I'll try and do it as quickly as we can so we can do office hours before the term test, but we are going to cover it on Thursday, okay? So give that a quick little read so that you're ready for Thursday, and then prep any questions that you have for the term test for me as well, and we can take those up, okay? So I'll see you later. Have a good week. Work on your assignment and study hard.